Welcome to our second webinar series on the fundamentals of descriptive research. Last month we tackled just some introductory topic on descriptive research, and we did PICO and study designs and why we do descriptive research, why it's important and so forth. And this month we're doing bias, error and confounding in descriptive research. It's our second webinar that we're doing live online, so welcome. And this is kindly hosted by the Emergency Care Society of South Africa. You can visit their website on www.ecssa.org.za. Also like to give a shout out to Cape Peninsula University of Technology, who are in partners with us, together with Open UCT and the Center for Evidence-Based Healthcare here at Stellenbosch University. If you'd like to tweet EXA, please do, and the Center for Evidence-Based Healthcare. This is also a free CPD event for anyone, and also it's OER, and thanks to Open UCT, it's Open Education Resource. So this resource, this lecture, you'll be able to find anywhere on the web, YouTube, UCT's website, and also at the EXA website. You'll be able to access this. So my name is McCaul. I am a researcher at the Biostatistics Unit, at the Center for Evidence-Based Healthcare. Always so difficult to mouth those big words. Shame. And today we're talking about bias, error and confounding. And this is a great topic, especially if you are new to research, because it's very important that we understand this. Because essentially what these terms, bias, error and confounding, boils down to is whether we know what we've measured, what we think we've measured, is actually the truth. And that is validity. Validity is how close is something to the truth, or is something actually the truth. And I love this saying, and it goes, God is the only truth. For everything else, show me data. So it really comes down to we'll never actually know the truth. We won't know whether something is actually true, yes or no. Especially in research, where we're trying to make measurements, we're trying to select people. And are we making these measurements correctly? Are we selecting people correctly? Are we comparing like with like? And this, to a certain degree, is always impossible. So thus we study this thing called bias, which is deviation from the truth, deviation from validity. Error, which is, we can say is just findings due to chance, and this thing called confounding. And we're going to be going through each one of these in this lecture. But before we do that, I want to let us think about this compass first. And this is what you see here. And we've got the compass. It shows to magnetic north, as we know. It doesn't show to true north. So, and that's kind of a bit of the analogy that I spoke about earlier, that we won't always know what the truth is. We won't know what true north is, even with our little compass that we have. But we can get to magnetic north, and that's close enough with a certain amount of precision. But there are things, those purple arrows, that can take our readings far off. It's like taking a magnet close to your compass. It's going to stuff up your readings. And these things that can hurt our readings we'll be talking about. So before we get into the depth of bias and confounding, it's important that we know, well, when we find a study result, what kinds of validity are we going to be looking at in this lecture? And you get two kinds. You get external validity and internal validity. So let's hypothesize that we have the world and we're interested in people in sub-Saharan Africa, or let's just say South Africa. And we've got a study question, which I'll introduce to you just now, but we sample from South Africa. And we've got some happy people, we've got some females, some males, and we've got an alien on top there. And either way, we sample them, and we have a question. And our question is, in patients with penetrating trauma, so either they got stabbed or shot, is spine immobilization a risk factor for mortality compared to no immobilization? Now, penetrating trauma is, penetrating trauma. Spine immobilization, for those of you who might not know, is when you put someone on a backboard, usually a wooden hard backboard, and you strap them up so that they have restricted spinal movements, restricted movement of the spine, and it's there to prevent potential spinal cord injury. or spinal injury. Now, remember, we're going to get some kind of study findings from this. But just to quickly recap, there are various ways you can answer this question. And the one is you can look at people with exposure who have been spine immobilized and people who have not, and follow them up forward in time until they die and see who dies. Obviously, the population is those with penetrating trauma, and they're either exposed to spinal immobilization or not, and we follow them up forward in time towards mortality. And that would be a cohort study, but remember, we're doing descriptive research, so we're looking at exposure and the outcome at the same time. We can't actually ascertain temporality, chicken and the egg thing, because we're, for example, looking at a massive trauma registry that was done in the EC, Emergency Care Center. And we can't ascertain whether which one happened first, the exposure or the outcome. So we're looking at the same time. We're literally looking at retrospective audit data, for example. So we're looking at a descriptive study. It's exposure and outcome. Now, okay, good. So now that's just important that we note that. So when it comes to external validity, remember we've got our study findings, whatever it may be. For example, you're less at risk or more at risk of dying if you were immobilized compared to not. Now, that result of our study finding, which is found from a sample in South Africa, like one province, for example, can we take those results and generalize it back to all of South Africa or sub-Saharan Africa? And the extent to which we can generalize back to our own population that we're interested in, or my population that I'm interested in, is called external validity. The external truth of our study. Can we generalize it? So external validity really is the ability to generalize from the study, the actual point estimate in the study, to the reader's patients, to my patients. And that's just taking the point estimate over to the population. And we can determine that by looking at the sample in our study and seeing how close is that, how close does it resemble our target population. And if there's a very good resemblance, then we can say, oh, maybe there is good external validity. Now, just remember that you can't just say, okay, great, I'm going to apply this. You have to now use the principles of evidence-based healthcare, which includes using the best available evidence, which your point estimate that you found in the study might not be, depending on the question you're asking. But you have to link that with your patient's values and clinical expertise, so the context. And then you can come to a decision whether this is actually worth something that I can apply. But external validity is a step just before that. So I just wanted to mention those very important three concepts of evidence-based healthcare when we look at external validity as well. So now, that's external validity. That's one type of validity, but we've got another one, internal validity. And internal validity has nothing to do with the target population. It has everything to do with the actual sample and the methods of our study. So, how do we know the results that we found, the study findings, is actually the truth, has validity? And that has to do with being able to define and detect three big things. And that is kind of a filter we have to go through. Is my results valid? Is it the truth? Well, we first have to look at our sample and say, okay, great, or our findings, and say, could what we have found here, could it have been to random error? Could it have been due to chance, what I found between the two groups? Mortality or not, between spinal immobilization and non-spinal immobilized patients? Could it have been due to chance? Is it maybe this thing called confounding, or is it systematic error? And those are the three concepts, random error, confounding, and systematic error, that we need to go through to be able to determine whether we have valid results, yes or no. If we can say that those three elements in general are not present, in other words, they're not introducing bias, skewing our results, then we can say that, hey, maybe we have the closest we can get to the truth. We might have valid results. And that is what this compass is all about. So we're going to be looking at what can take this compass needle off path. And we'll be looking at random error first, then systematic error, and then confounding. So let's see what can take this compass off. So remember, we have study findings, and now we're looking at what could take it off path, off our estimate. And let's look at random error. So let's imagine for a second that you're in a lecture theatre. And here's me, I'm lecturing you, and we've got a couple of people that have joined us online. So imagine you're in a class. And I want to know, what is the average height of the people in this class? And I take a sample. It doesn't specifically have to be random. I go to one side of the class and I take a sample. There you go. And I find that the average height of those 4 people in that sample is 1.5. Let's say it's 1.5. Now, great, that's good. And in that sample, there's variation. You know, someone might be 1.4, 1.5, and 1.6, but the average is 1.5. Now I take another sample, and I find that, no, actually, it's 1.6. Gee, well, why a different result? And it's actually just a very logical answer, and that is that we've got normal biological variation in between people and in samples. No one sample is going to be exactly the same if you're sampling different people, because there's natural biological variation. And let's say, for example, we wanted to know if there's a difference between height stratified by sex. So whether if you're male or female, you're taller in the one group compared to the other group. How do we know what we really found between males and females? Let's say my one sample here on the right was from males, and it was 1.6. And my first sample was from females, and that's what was 1.5. And I've got 4 in each group. How do I know that difference of 0.1? How do I know that difference is really real? How do I know it's a real difference? Well, the difference we found in the sample is natural. That's random error. It's variation that we're going to find. It's just difference we might have found by chance because our sample size are so small. If we were to take a bigger sample size and another very big sample size of males and females, and we found a difference still, then we might be able to say, maybe there isn't actually a difference just due to chance. No, there might actually be a real difference between these two groups. So the concept to remember is that random error is something that happens naturally. There's natural variation between groups and in between people. And if we find a result and we find, okay, great, how do we know this is really different, or that we find a difference, then it could just be due to random error. It could just be due to normal variability in our sampling and the people that we sample. So how do we know that there actually is a difference between two groups? And that's where statistics comes in. We can test whether what we found between the two groups was really due to chance or not. Was it really due to random error or not? And that's where the p-value comes in, for example. To a certain degree, it tells us what is the probability that what I observed is due to chance. And something that can decrease random error, just the normal variability we get between samples and so forth, is sample size. Because the larger our sample size, the more inclusive we are, the more generalizable it will most probably be, and the more valid will be, and less variation we'll have, especially if we're comparing between groups. Another concept is, if I went to the one side of the class here and I just kind of picked up the people I liked, that's a bit of a biased sample. I'm introducing a form of selection bias, but how can we try and limit that? And this is this concept of sampling, and you get 2 kinds of sampling. You get random sampling and non-random sampling. Non-random sampling is what I did in the class. I conveniently just went to the one side of the class and conveniently sampled the guys that were closest to me. I could have done another way called snowball sampling, where I sample one person, I say, choose your buddy next to you, or choose a random person that you would want to also be included in your group. And that's non-random or non-probability sampling. The other one is probability sampling, and this gives us the best estimates of a group. So we can have simple random sampling, which is just taking a list of people and putting that list in a hat, for example, and drawing out, let's say we have 100 people and you draw out 50 people randomly from the hat. So it's like a same probability as a coin toss. You have stratified random sampling, where you stratify people by sex, for example, in our previous example, males and females, and we have a list for each, and we sample people randomly from those two strata. We also have systematic sampling, where we start from a random number, and then we systematically sample every kth person from that. And sampling helps us to get more representative samples. So in my previous example here, if I took random samples of everyone in the class and I stratified by male and female, then I'd have a more representative sample to compare, because I'm not just taking from one corner of the group compared to the other corner of the class where the taller people might be sitting. For example, if I take people from the front compared to the back, much shorter people might be sitting in the front compared to the back, because all the tall guys are at the back, because they don't want to be in the front, because then the short people scream at them. So if I take a random sample, I would have eliminated that kind of chance findings, random error findings. So that's important to think about when it comes to sampling, that random error is one of normal biological variability, and you're going to get variations between samples, and it could be due to chance, called random error, and we need to try and minimize that through increasing our sample size and sampling correctly. Right, so that's in a nutshell a bit of random error, or just chance findings. Now the next concept is very important. That has to do with systematic error, an error that we introduce as researchers, where random error is not something that I can actually limit. Yes, I've got my sampling strategies, but I'm always going to have some kind of biological variability. I can't actually account for that except for increasing my sample size. Now, systematic error is divided into two groups. You get selection bias, selection error, and information or measurement error. And that's the two main categories of systematic error, the two things that we can introduce as researchers, where all other kind of biases that you might have heard about can fall under. Now, it's important to note that when you think of biases and selection bias and information bias and recall bias and all those weird things, and measurement error, or random error, all those things are actually just absolute natural phenomenon that occur in everyday life. It's because we're measuring people and because we're doing research that suddenly this has become a problem. Otherwise, it would be natural things that we can understand and relate to in everyday life. And so it's important to keep that in the back of your mind. The only reason why we have to study all these bias and errors and things is because we're actually doing research, and we need to try and be as objective and empirical as we possibly can. So we need to account for all the interactions that we might have in life, and that's what we're trying to quantify here in bias, error, and confounding. So selection bias stems from an absence of comparability between groups being studied. And that's systematic error. It's an error, and the subgroup of it is selection bias. And so it would be, for example, let's say, for example, we're comparing those who are immobilized and who are not immobilized, and looking at mortality as our outcome. Those two groups of people we're comparing, of those who had penetrating trauma injuries. So let's say, for example, that my two groups actually were selected differently, and there is non-comparability between groups. Those that were immobilized look fundamentally different to those that were not immobilized. For example, there might have been more stab wounds in the immobilized group compared to the non-immobilized group, or more gunshot wounds in the immobilized group compared to the non-immobilized groups. The mechanism of injury might be different, or the injury severity score might be different. And you can see that those things is going to decrease the comparability between the groups. Because if you were stabbed or shot, you're most probably going to die, more at risk of dying than not being shot or stabbed. So if there's non-comparability between groups, and that's how we can identify selection bias, is that we can't compare these two groups. And that's a big thing about comparing groups, is you have to try and have them as balanced as possible. But if there's imbalance, then you've got some form of selection bias. So the method of how you selected those who are immobilized compared to non-immobilized differs. For example, here we have this table 2 of a study that did exactly that. They looked at people who were immobilized compared to not immobilized, and they looked at their mortality outcomes. But first they looked at, well, let's just see if these groups are actually comparable. So here we can see they looked at race and age, and we can see that some of the things are different. Those who were immobilized compared to non-immobilized were ethically quite different. Same with age, there were some range of age differences there, but those aren't necessarily big predictors of the outcome or things that might influence or introduce selection bias. But there are some other outcome measures that we need to look at. So here you can see that people were far more stabbed in the, let me have a look at this, in the non-immobilized, non-immobilized group. There were far more stab wounds in the non-immobilized group compared to the immobilized group. So if you look at this, the non-spine immobilized group had more stab wounds, and they in general had higher revised trauma scores than the other group. So that's already a form of selection bias that might be coming in. The injury severity score, basically 0 being you're fine and 25 being you're very, very close to being dead. There was more in the spine immobilized group. So here we can see there's imbalances between groups. There's a form of selection bias here, and that's a fundamental flaw of observational research, is that there will always be a form of selection bias in observational research, because we can't assign people to either be immobilized or not immobilized in penetrating trauma to balance the groups. We can't assign them randomly. We can't do that. We have to just take what we have. And there's going to be differences between groups. So we have to try and adjust for these differences and see, can we really compare these two groups? So here we can see also there's pre-hospital procedures, which we know is, if more people were intubated in the one group compared to the other group, they're more likely to possibly die or were more severely injured. Same with IV fluids. It might take a long time to put up fluids. And you can see there's differences between groups. And so the question is, are these groups comparable? And it doesn't specifically look like it. And also, is there anything missing? So just quickly, you can see the p-values there showing actual significant differences. But it's also important to ignore the p-values and look at, is there clinically significant differences, not just statistically significant differences. So is anything missing? What would you say? And if you can pause this video, pause it and kind of go through the list again and see, well, what else would I also want to know that could influence my decision regarding selection bias? And the answer would possibly be that scene times. How long did they actually spend on scene? Because obviously if you immobilize someone, you're going to spend longer on scene compared to not. And how long did the non-immobilized people actually spend on scene? So something nice, something important to look at. Not all studies measure all the things. And that's selection bias. Non-comparability between groups because of some inherent bias in how we selected people or included people in our study. Now the other form of systematic error is information or measurement bias, and that results from incorrect determination of exposure or outcomes or both. So it comes with, how was the outcome measured for this study? Did they look at mortality in the same ways? Did they define it in the same ways? And that is a very general statement because you can apply it to all kind of studies. How did you measure the outcome? If you're looking at height in people in that class that we had earlier, were you eyeballing it? Or were you using a tape measure? Were you letting all people take their shoes off or not? Did you have all the women have their shoes on and the men not while you used your tape measure? Did you maybe introduce a measurement bias? Were the groups measured in the same way? Did you give a questionnaire to one group and an interview to the other? if you measure people differently, you're going to have different responses. You're going to have different point estimates between groups. You're not going to have comparability, which is what this all boils down to. And you're going to introduce measurement bias. So, for example, how is immobilization defined? Was it full spine immobilization? Was it immobilization in the sense that, we just needed to carry the patient from point A to point B, from the car wreck to the ambulance, and that was now immobilization because he was on a backboard? So how was immobilization defined is important, and the exposure, how is the exposure defined? And this can be attributed to, generalized to all study designs, and it's important that you look at, am I measuring stuff the same? Am I measuring it in a valid way? And do people understand what I'm measuring? And that's systematic error. And remember, or measurement bias. And systematic error can be divided into selection bias and measurement bias, or information bias. All right. And you have various other forms of bias, but they can be grouped into either information or selection bias. Differences in how we select people. Right. So remember, we've gone through random error, we did sampling, we did a bit of systematic error now as well. And now we're going to go through this concept of confounding. Now, confounding means to confound. It's a Latin word, and it means to pour, actually, to pour, like pouring water. And if you look at a bottle, a glass of water, and you can see straight through it. Now, confounding is actually just saying that we're pouring coffee into that glass of water, where you could see right through it, but now you've muddled the effect. You've muddled the waters. And that's confounding. It's an extra factor that's blurring the effect between what you're trying to find, and between the exposure and the outcome, for example. So confounding is a mixing or blurring of effects, and a researcher attempts to relate an exposure to an outcome. So what we're trying to see is, does immobilization, is it associated with mortality compared to not immobilizing? But we might not actually be, and we might be finding some kind of result, but actually there's a third factor, a third variable, termed a confounding variable, that's actually influencing our outcome. That's actually causing this result that we're seeing between the exposure and the outcome, but it's actually not due to the exposure and the outcome, it's due to the confounder and the outcome. And that's confounding. And confounding, let's say, for example, we're looking at exposure, which is immobilization in our study here, and we're looking at outcome, mortality, death. But now we have this confounding variable. For example, the patient might have been immobilized, but also he was quite hypotensive. He had a really low BP. And we know hypotension is causally associated with mortality. It's on the causal pathway. However, whether it's not necessarily on the causal pathway with immobilization. And this is part of the definition of what a confounder is. Confounder has to be causally associated with the outcome and just normally associated with the exposure. So it might be that immobilization influences your blood pressure. So there's some association between immobilization and hypotension and immobilization. But now we might be finding a link between the exposure and the outcome, but actually it's just hypotension that was causing the mortality. So what other kind of confounders could we have? We could have anything like sex, for example. Your gender could influence mortality, and it could be associated with whether you get immobilized or not. Who knows? And these are the things that we should be measuring in our study to reduce the mixing of effect that we might be getting between exposure and the outcome. Because you might actually say that the exposure is associated with the outcome, but it's not. Something else is influencing your effect, and that's the confounding variable, and you need to measure it beforehand. So to be able to adjust for it. So there's two ways we can look at confounding or try and minimize it in our studies. And that is with regard to stratification and adjustment. And stratification is where we stratify covariates or confounding variables before we do the analysis, put it that way, where we can maybe say, okay, great, we think that people who have hypertension compared to normal blood pressure, compared to high blood pressure, might have different mortality outcomes. And we now divide the people in those groups beforehand, and then we can analyze them using stratification. And that is a great way. The other way is, and thus for stratification we eliminate this confounding variable because we matched or stratified earlier. The other thing is we can adjust. If we don't do stratification, we can adjust in the analysis. We can say, great, there is an exposure and an outcome. Let's introduce this other variable which we've measured now, hypertension, into our exposure outcome kind of model. And we can say, if we place hypertension in that model, we keep it consistent in our model, then we can adjust for it. We can say, okay, great, including hypertension in this theory model that we have, does exposure still influence the outcome? Or is it actually just hypertension? And so that's called adjusting. And it's a statistical method that we use. So here we can now just take a step back and think confounding. Great. It's a mixing of effect. It's a third variable coming in that might be blurring the effect between what I'm looking at originally. So here's an example of the odds of death for people who are immobilized compared to not immobilized. And if your odds ratio is above 1, then your odds of dying are more in compared to one group compared to the other group. For example, in this case, you're more at risk of dying if you're immobilized compared to not immobilized. And so, for example, you're 2 times more likely or not. If the odds ratio and the confidence interval stretches over 1, then there's probably no difference. And this is a different theory. This is a biostatistics. And if you're doing your masters and so forth, please do pay attention to these concepts. And I would advise that you maybe speak to the SIG and we can guide you in some resources that you might need to understand this concept. But either way, in a nutshell, that for all patients in this graph, you can see that their odds ratio was about 2. It means that for all patients, you were about twice as likely to die if you were immobilized compared to not being immobilized. And what this thing is, figure 1, is a multiple logistic regression. So what they did is they adjusted for all these confounders. And they said, despite all these confounders that might influence the association between the exposure and the outcome, there was still a mortality difference between the two groups, even adjusting for the confounders. So even adjusting for ISS of less than 15 and so forth, there was still quite a high odds of death. The same with being hypertensive. Adjusting for hypertension, they were still found that there's a significant difference when it comes to death, and for gunshot wounds and so forth and so on. And here you can see that overall there's still risk of death. In the end, the odds ratio for dying for spinal mobilization was 2 times more likely to die. And the 95% confidence interval ranged from 1.3 to 3.1, which means that we're 2 times more likely to die in the sample. But how do we know that's true in the population? And we can be 95% certain that the true population value, or the true population effect measure, odds ratio, lies somewhere between 1.35 and 3.13. And interestingly enough, for this study, they also calculated number needed to treat and number needed to harm, and you needed to treat about more than 1,000 people to prevent 1 death, but number needed to harm, you only needed to harm about 60 to 70 people. You only need to treat about 60 to 70 people with immobilization to cause 1 death when it comes to penetrating trauma. And that's some really hardcore statistics and measures of effect that we can take home to understand that is spine immobilization really doing so much. So if you look at the study, yes, they had some selection bias, they might have had some measurement biases. Doesn't look like there's any measurement error. They had a massive sample size of thousands. They did adjust for confounders, but not all of them. But I think we can be relatively certain that spine immobilization in penetrating trauma actually does cause more harm than good when it comes to mortality. And that is confounding, error, and bias when it comes to descriptive studies. And that's a bit of a nutshell. If you want to know more, please do contact the SIG, myself or Willem Stassen, and you are welcome to communicate with us through communication@exa.com. I think please just have a look at the website to confirm that. So just one last shout out. Thank you very much to Open UCT, CPUT, the Emergency Care Society of South Africa, obviously, and the Center for Evidence-Based Healthcare, Just one last thing, if you would like CPD accreditation for this lecture, please join us at our website. If you're an XM member, you just fill in the quick questionnaire that we've made for you, and based on this lecture, and then you'll get your CPD certificate emailed to you instantly in PDF. And also have a look at Sanguine, our biannual publication, professional magazine for paramedics and anyone who's interested in learning more, clinical practice, research, teaching, evidence aids, anything you'd need in a professional magazine is in Sanguine, so please do visit the publication. We publish biannually, also available on the EXA website, and you'll get the latest version if you are an EXA member. So that's me, Michael McCaul, and please remember our next lecture, which will be around about in between the 22nd or 25th of next month of April, and we'll be going through data collection forms and how to make them in descriptive research. How do we make valid ones? So now I'll be opening up the floor to questions. Please do post your questions. I see there's already some questions being posted on the forum, but for now, for the video recording, thank you very much. This is me, over and out, from the Emergency Care Society of South Africa, Research and Development Special Interest Group.